So we really have to revisit what it is we're trying to do here, right? A lot of it is about building the open tools and modernizing many aspects. So anytime we build a useful work product that other people can reuse in other contexts, that's a success for us. So whatever you are building, always think about whether or not it's some general modular tool that somebody else can reuse in some other context. And if so, then we should work hard to make that actually reusable. So we want to modernize this whole process, because anybody who's tried to set up something recently using GAF types has dealt with, like, Antichamber is this weird collection of very old C programs that happen to work together in some sort of absurd way. There's 5 different places that improper torsions are defined in different C files, I believe, in Antichamber. So it's completely nuts. So we want to simplify all of that and use some modern software design to help us do that. We want to curate open data sets. We've been talking about what license models we'll use for how to license the code and license data in ways that are maximally usable to other people. And then we also want to make sure that the force fields that we generate are open and very useful, with the idea, as David said, that we start with something that's a good starting point. And it sounds like Smirnoff is no worse than GAF, which is not the greatest selling point, but the fact that it's so short makes it very easy to work with. So we think we can rapidly improve it, especially leveraging things like force balance, which has already produced a great protein force field and some great water models. And so taking advantage of that and optimizing just what we need, we can target improvements on rapid release cycles, get things to industry and in their hands so that they give us feedback, start to use them in our own groups, and then really improve the accuracy in rapid cycles, with the idea that whatever we're doing, we're automating that so that we can always easily make it better the next time around. We can do everything we've already done and more each one of these cycles. So as we work to get more density calculations in to help improve things, we add that into this modular framework. So that sounds...
Does this limit people only to use OpenFF? Or...
No. As David said, you can convert from this right now using a mixture of parmed and intermol to every...
I mean, if the functional form changes, mixing rules change, then...
Great question. I'm going to skip ahead to exactly what that is. So what I will tell you is that we've made a ranking of what we think is important to achieving accurate. Our goal is to be as accurate as possible, because what you enable with, like, going from 0.9 to 0.8 kcals per mole in accuracy is enormous, right? Especially getting from 0.5 to 0.4 is going to be really hard, probably requires polarizability. But we listed everything that we thought might be workable for improving Smirnoff, kind of ranked it from easy to hard. And this is a great thing for us to discuss this afternoon. If we think this is reasonable, selective polarizability is probably at the end, because it's much harder to do than just refitting the torsions or tweaking the Leonard-Jones based upon liquid mixture data, things like that. And if you separate them into 2 classes, if you re-optimize all of the Leonard-Jones, then you're going to break compatibility with existing force fields, existing amber force fields. And then at some point, when you start getting into, I don't know if you even have it here, but different functional forms, then you start to actually break compatibility with existing codes. And we want to do that at a time where we have enough lead time in order to work with the tool makers to make sure that they can accommodate different functional forms. OpenMM is great because the custom forces allow us to do all sorts of crazy things, try new force types, and if we can justify that, it's going to be so much better. Then we can actually work with the tool makers to incorporate these things into their codes. But we want to make sure, especially for the industry partners, that they can use whatever code that we want. But we can go a far way without breaking any of those things for right now. So let me just come back to this. David already showed something like this, though. We're targeting several compute infrastructures here. We all have local GPU clusters, which are lots of GPUs we can work with to do all sorts of great things, including QM. We're targeting some NSF Exceed resources through our NSF Tiny grant with Michael. We can actually write for NSF data that we can all use on this project. We're trying to get funds for essential cloud operations that allow us to use, like, testing on Travis and things like that, and hosting distributed databases, using tools in the cloud to reduce our infrastructure needs of having actual physical disks or having database servers that we maintain ourselves. And then we also want to allow us to use GPU computing, either Google Cloud or Amazon, to, when we need to do a ton of computation at the same time, have access to those resources. And a lot of this has come down to, it's difficult to get a collaboration of this size to actually work together effectively. And part of the reason, I don't know if you've all met Daniel Smith here. Maybe you can raise your hand. So Daniel works with the Molecular Software Sciences Institute as a senior software scientist, something like that. So MOLSI is this $30 million NSF-sponsored initiative to really try to help the entirety of fields dealing with computational molecular software or software for the molecular sciences do a better job of making the software interoperable, making it maintainable, making it sustainable. And so we're hoping to work closely with them to use best practices and to really even pilot some ideas that might work for other larger collaborations, but make it easy for us to make sustainable software and make it easy for us to collaborate with each other. So we've envisioned this as having a coordinating software scientist that will work closely with MOLSI to make sure that we're in sync about what infrastructure MOLSI might be able to help support as well, or at least make recommendations about how to coordinate with the larger community, but as would also be the central person who interfaces with industry in terms of doing support. I know none of you on the academic side probably want to deal with industry directly in the sense of supporting when things break, though some people enjoy solving those problems, but it's really not the first task doing science. Doing science, we really want to come up with new tools and new features and new ideas and really explore different aspects of this in bite-sized chunks that we can also publish, which is important. So we're thinking that most of our development will happen in separate project repositories, and that will then work their way back into the central repository, which is the Open Force Field repo, which has all of our major toolkits that are robust enough to deploy. And so anything that's a generally useful feature will generally end up in the Open Force Field repo. Maybe that will change a bit later, but that will be coordinated through the software scientist who's going to take your pull request and work with you to make sure that everything is up to speed, that you've got the right, a nice clean API, that you've got the right kind of tests, the right kind of documentation in place. It's going to be a little bit rough to all get ourselves up to the same kind of level for how we do these things, and working at the process is something that we should be discussing these 2 days as well. But I think a lot of you are already doing this already, so it's not going to be too hard. The other thing is that the software scientist is supposed to make sure that they help architect the central parts of the API to make it clean and interoperable. So if you're working on a module, then there will be a simple API that you would plug into that will let you do whatever you want under the hood as long as you conform to the API on the outside. It'll make it easy to interoperate with the other pieces as they come together, because all of these, especially the Bayesian stuff, has to interoperate under the same hood. Same thing with defining specifications, reviewing pull requests, and helping develop some key infrastructure in collaboration with other folks. Does that sound somewhat reasonable? And the enemy here is always entropy. If we're doing things 15 different ways, even within the same group, it makes it very, very difficult. So standardization of all of our practices, tools, even the way we do testing is going to be really important. So it might seem a little bit weird, like why should I have to do it this way? But it's going to make it a lot easier for us to be able to collaborate. And some of these ideas are also being used more broadly. So we ran a software summer school, or Daniel did, last summer, where a lot of folks who are developing computational chemistry software as part of their PhD came out and learned the essentials of GitHub and Travis testing and coverage testing. So these are principles that will generally allow us to collaborate as a community much more broadly than this specific collaboration, but they're also going to help you get a job if you ever want to go into software development or anything else where they're printing money in machine learning. All right, so what
if I can make a small comment on that, that's actually something else that we as a group and John's group have been trying to focus on, is coming up with good documentation for standard software development practices that we can hopefully pass on to incoming grad students, incoming postdocs that don't necessarily have the experience for this sort of thing. And that was something that we discussed. I might have given a small talk on, but that's outside this particular scope. But it is something we are working on if anyone wants to talk about that later too.
Yeah, Levi and other folks in the lab have assembled some nice, it's just very basic, very minimal, but it's meant to get you up to speed with what the main practices are and why. Like how to set up a Python repository so that you can do Travis testing and conda deployment, things like that.
Levi, do you want to put a link to that in the meeting channel and the Google Doc?
That sounds great.
Yeah, I'll put that in. I'll drop that in.
Thanks.
Let me just say on behalf of industry, it's maybe a few industry guys here, maybe Heidi could speak to this as well. It's something that industry really cares about more and more. I got away with not having very good software practice for a while. They're taking it back by the shed at the same time. But for hiring now, it's actually really important.
that's not only the pharma industry, but all of the software industry in general, or data science or machine learning. It is important. I hear this time and time again from folks that work for Etsy or Stitch Fix, that having well-documented code that has unit tests. If you go to they're going to look at your GitHub page and they're going to see whether or not that Travis badge is passing. And if you have no Travis tests, it might not be so great.
The industry really is liking the gamification piece. If you don't have 3 or 4 badges on which your projects are just going to kind of pass on by, because that's kind of the proof of these best practices. It's interesting.
So hopefully we'll hear some more targeted recommendations from Daniel tomorrow morning too.
I'll make one
Yes.
comment here. I think one thing industry is also picking up is workflows. I think that's another experience I think most people coming in don't have. Because how to make workflows of all the code you're writing, because you
Yes.
write different packages,
Yeah.
and then you write a script
Yeah.
to run these. And
We
the script will be lost after a year.
we had this is what industry fears, is that bringing new technology in is only going to last as long as the person who has brought that technology in. As soon as they leave, then they don't know how to use the tools anymore. So this is something we've spent a lot of time working on. We had a San Francisco-based whole workshop on this that I still have to write the report for. But that's something that's very serious, that now the technology exists to put things inside of Docker containers to make sure that they plug in. And to their credit, OpenEye has been producing a really nice workflow engine called Orion that will at some point be free for academics, that has enabled a huge amount of science by hiding all of the detail of this infrastructure and making it very easy for tool makers to deploy their tools in a way that interoperates. But this is something as a community we need to solve much more broadly and have some standards for. All right, so what are we delivering? All of us are going to be working on different aspects of the toolkit. We'll be eventually producing parameters we want to deploy. There's data sets that we're going to gather and recommend to be used in a compatible manner. We're working on ways to standardize some of the best practices that we use to collaborate with each other. We're already talking about how we're going to get molecular topologies represented on disk if you have to share them back and forth, because PDB is a terrible, terrible format that should have died long ago. But unfortunately, PDBX and MMSIF are not any better in terms of representing the actual chemistries. The best thing we have right now for understanding what's in a PDB file is actually a bunch of OpenEye generated Mol2 files that you can download from what's called the Chemical Components Library on the PDB. OpenEye, out of the goodness of their heart and their frustration, I'm sure, of the blood boiling in there.
Well, goodness too. But
Yes.
A lot of
Produced all of these, so every residue type appearing in the PDB has a representation in the Chemical Components Library, thank goodness, which actually tells you what it is or what it's supposed to be. Documentation is very important. It is also very important if you ever want to get a job afterwards. And then publications, if you want to stay in academia, of course, are very important. We want to make sure that everything we do can easily be and rapidly reported as a bite-sized chunk we don't all have to be co-authors on. It can be subsets of people. All right, so the major efforts we have in terms of toolkits are this Smirnoff force field typing engine, right? It has to assign the force field parameters to a topology based upon the specification that we have, and the specification is supposed to be backward compatible through different generations. The APIs should standardize how we create systems so that in principle we could have other non-Smirnoff based force field things in the future, and we just want to have a nice clean way of very simply creating these systems in Python. So you could think of this force field API concept as being broader than just Smirnoff. We think Smirnoff is great and we should use it for a little while, but there might be other ways to do it, and we should just keep this API clean. We want a topology representation and interchange format for describing what it is you're trying to simulate. If I have a box of some proteins and some nucleic acids and a bunch of random modified amino acids are in there somewhere, and I have waters and co-solvents and some small molecules, and I want to do some sort of calculation, we should have a way of representing that in a manner that preserves the chemistry. And that doesn't exist right now, really. So we've been talking about how we're going to produce that. And I've been working on a topology representation that's at least an object representation in Python, and we might have to coordinate how we actually interchange this with other packages as well, but there'll be some way to get that onto disk and some way to construct it from existing information like PDB files and Mol2 files. There's a physical property calculation. I already alluded to this before. We need some way to have all of these different levels of this physical property calculation that can go to deeper levels if it needs to do more simulation. We need a very simple, clean API that explains how this interfaces with things that are built on top of that optimize the parameters or actually sample things. And then the APIs internally for the different layers so that we can stack as many layers as we want for these surrogate models. or this is one of the reasons why Daniel is here too. He mentioned that data is the new oil. It really is important. There's lots of value in making sure we organize the data. It doesn't make any sense to have to repeat all of these QM calculations over and over again, especially if we're talking about like 6 million fragment calculations or something like that. They're expensive, and we should just store all of that data somewhere and make it easily accessible. Daniel has already produced like an amazing pilot project where you've reproduced how many calculations?
I don't know, like 30, 20 million.
Yeah.
Check versus project.
So he'll tell us a bit more about that in the morning, I think. But if we could build our own QM database to store anything that we think we might need and then be able to mine that later on, it'll really help a lot of our research, as well as if other people can plug into it and contribute as well, it'll keep growing and be more value for us in the future. There's many things, not only just torsions, but also conformational energetics that Christopher has suggested. We might even be able to calculate things like protomer and tautomer energies in the Bohr-Oppenheimer approximation, even dimer cluster energies that Li Peng has found valuable, or electrostatic potentials. All of those might be things we might want to store. And then finally, we need some sort of optimization and inference engine. Force balance is one of those engines already, and we need the Bayesian inference stuff to be built on top of that in some sort of clean way. So am I missing anything, or is this sort of the...
I have a,
Yes.
I don't know if you want a question, but on the QM database, I mean, it seems like ideally the database, with the amount of effort that would go, would be something that would be usable by the larger research
Oh yeah,
community.
absolutely.
And so I guess, would there be a thought about collecting input from people as to what's the right level of quantum and what like calculations to do? Because you could put a ton of effort into it and then have something that only a few people end up using versus...
I think what we need, and so Daniel's already learned some of this, that
Yeah.
he'll share some wisdom tomorrow, but
Okay.
for us, we need something that's a little bit or extensible, right? We don't want to be wedded to something and have to deal with tables all the time, but just meets our needs, but could grow a little bit further beyond that.
Yeah, so let's talk a little bit about the various representations and the issues with each of them. There's a lot of different ways to do it, a lot of approaches. It depends on exactly where you want all this to go.
But you're also asking about what type of QM calculation you're doing. If I
That's more what I
understand
was referring
you.
to.
Vicky will say a little bit about that, but
Yeah.
presumably Daniel also has thoughts on that.
Yes, I mean, like the database that I have, it is built to run many different types of computations on the same set.
Oh, wow.
Yeah, and then you cluster those based off molecules that are similar, like different computations are like. And so I'll go through it.
Cool.
But there are some representations that are very flexible, so that they could be like but still allow you to grab like, give me all the calculations where I have a torsion drive for this level of theory when you're mining them. Or if you don't, then you can make sure they get queued up, and Amazon Batch will do them for you. So there's.
And that's where it gets really smart, because you say like, I want this data, and it's like, well, I have half of what you want, and so you're like, go compute this for me, and like I'll check back in a couple days.
Cool.
So I think it can be flexible, and the infrastructure. There's so many tools available in the cloud right now that the infrastructure can really be minimal, and we don't even need a server running all the time. It's just per query there's something that's spun up. Sorry, am I missing anything else from this horizon of toolkits? Because it's important for us to get it on the roadmap. Yeah.
I just have a small comment regarding the QM databases that I think that a lot of calculations that we're interested in running are often specified in terms of continuous variables, right? As in like the positions of atoms, and I think that means that very often you would want to run a calculation that is extremely close to one that exists, but is not exactly the one that exists. Does that make any sense? So suppose you are working on a geometry that's not part of S22 or HC10 or something. You just want to find energy and gradient of that structure. I think a useful method should be able to say we don't have the exact calculation.
So an approximate
but we found
query,
one that's very close.
I think that could be easily because if you're already defining hashing on the chemical species, right? It's a very easy query to go and do some distance calculations. I think that's probably an easily solvable problem that could be we want to make the database modular so that you can have a simple API for querying in different ways. It would simply be an easy thing to extend it to do something like that.
John, I wonder about bullet 2, topology representation and interchange format. That at a low level, I understand what you're saying at a low level, but then kind of similar to some of the discussions we were having, you've raised some points also earlier about biopolymers and how we perceive those. But I would also say something that's been coming up for Gaetano and myself at OpenFF. We've been how to use Smirnoff is kind of a game also what Harry was talking about is when you're beginning to intermix different models.
Mhm.
And intermixing different models is not just topology representation, it includes topology, but for example, just if we change the mixing rules
Yep.
for something, then we could still use, amber for just the protein because we don't want to mess with that.
Yep.
We could still use whatever we like for intramolecular of the molecule, but where the molecule mixes is going to have its non-bonds with the protein.
Yep.
Then we just have to figure out to convert in between those so you can block out sort of the n-squared matrix, if you like, of different domains of interactions.
Yeah.
It's topology representation, but at this level, which isn't just molecular, it's at these.
That's something we should discuss explicitly, I think, because a lot of this framework assumes that you're just parameterizing some component of the system or the whole system, but I want to parameterize different parts of the system with different things and then mix them together in some interesting way can get very complicated. So
So
we should.
does that go under the topology representation, or does it deserve something?
I think it's really at the level of like the force field is meant to take a single topology, right? And if you want to have different force fields applying to the same topology, or do something more complicated than just like parameterize something in gas phase and then pull that into with ParMed to something else, then I think it's going to get more complicated. So we should block out some time to talk about that. Can somebody make a note of that? All right, I've already gone through this list. I've put the PDF already in the Slack, so please look through it. And if you have any comments or criticisms, let me know. But essentially, there's one generation, which is this is all something that could be used with Amber force fields, because we're not changing the all of the Leonard-Jones, right? We're whatever we're doing with the Leonard-Jones, we're doing in the context of amino acid side chain surrogates or analogs that have to interact with whatever small molecule Leonard-Jones we're tweaking. But as soon as we start breaking that, then we're off into our own world where we have to deal with Amber derivative force fields. Now, Leaping has produced a very nice force field, probably one of the best Amber generation-like force fields, and already has a lot of the tools to do that sort of reparameterization. So it's not really far off to say start with that and then make it better by making it more compatible with the small molecule force field. So I don't think it's going to be a huge problem, but it does divide us into two generations. So this is sort of what we were aiming for. We wanted energetically compatible with Amber biopolymers for the first, and then incompatible for the second generation, with the idea that there's different sprints we could think of that are different discrete sets of things where lots of stuff is happening at the same time. We start with where we are right now, and then we're going to benchmark things and figure out how accurate it is. I think it's already a good way of the way through that. We'd like to do it for some binding affinities too. I think that's going to be super exciting, not just host guest, but also for protein ligand. Then we'd start to refit some of the Leonard-Jones and then the torsions, ideally. And then finally refit some of these bond charge corrections, because we're going to have to change those once we start changing the Leonard-Jones. That's what I was thinking. This is all up for discussion, obviously. We might need more types because we have a minimal set of types right now in terms of torsions especially. So when I say types, I don't mean atom types, I mean any types. Then it sounds like there's great work going on the host guest side of things, where we'll have more host guest thermodynamics to help constrain things and bring them in at the same time. That might even be a lot faster than on this, especially if water is involved.
So just to, why are we showing this? Partly, if you're involved in this effort, you're going to think you're going to be involved in this effort. As he's going through this, think about what is it that involves you or should involve you, or you have an interest in helping to make sure it doesn't derail. And then later we're going to be trying to kind of group people up into who's going to be working on this and who's going to help them with it and whose work does it overlap with, and having you plan how to do these things. So
And then,
think about where you fit.
there's a lot of dependencies here. Obviously, to refit the torsions, we need some way to get lots of QM data in the first place. So we need to build a QM database and do lots of QM calculations before we can refit all of the torsions in the force field, right? So these dependencies are going to come out of exactly, this is just the time we want to add in whatever is in each one of these. And then at some point we break with the Amber-compatible biopolymers, and we're also talking about improving biopolymer force fields at that point, and hopefully going beyond what has already been done by adding in more protein experimental data, like we could add in NMR data or other things at that point. I was just trying to express like all the parallel tracks that are going on at the same time. We need some automated QM fitting tools before, so this should be right over here in refit torsions. But essentially, we need to be building the QM database and building or starting to compile some of these things that can always grow with time. We want the database to be self-sustaining and be able to contribute more things to it as time goes on. Automated BCC fitting, in order to actually be able to put that in at this generation, we'd have to start over here on actually finding a way to improve or optimize those parameters. There's a lot of the Bayesian framework that we're already starting on, different model experiments, but it won't be really ready to refit the entirety of the Leonard-Jones until much later, for example. But it'll take a lot of engineering up to that point to actually get it to the point where we can bring it into the main code path. And then lots of other physical property surrogates models are going to have to be developed for some other things, like if we want to use speed of sound data, for example, we have to develop a good way to compute that and a good way to analyze the error, for example. There was also opportunity, like the cool thing about the industry consortium is that there's going to be a lot of people from the industry side who are really enthusiastic, expert computational chemists, and will have no limit in the feedback they would like to give us. So we'd like to take advantage of their expertise and take that feedback, both in terms of what they feel is important and in terms of the failure cases that they identify and what kinds of chemistries they're interested in. They might be interested in very exotic things that we hadn't even thought about, and take those opportunities for feedback. And we're not sure what the form will be, probably some meetings and get-togethers, probably some virtual meetings as well, and then some reports that we get feedback on. But they're fantastically brilliant people, and I think we should take advantage of them. So here's basically what we were thinking, depending upon how much funding they put together. I think 600K is still the very low end of things in terms of the slow model. But it could be that more people sign on as time goes along. So we might actually be able to be above the 1 million mark at some point in the next year or two.
And one way or the other, 600K is a lot better than zero.
It's a lot better than zero. That's definitely true.
And these things tend to snow. It's either an all or nothing thing. People start getting in, everyone's like, oh, how come we're not participating?
Yeah.
So if you get a critical mass, then
So
if
what
you get
we're
a critical mass and you start producing useful stuff,
yes.
there will likely not be a lack of funding.
And I think that's
if you
what
don't produce the useful stuff, it will dry up quickly.
that's what we're hoping for, is to get this critical mass going to begin with, because then we can actually get started. We are already starting with the assumption that this will. I mean, we're so far in with the legal paperwork that we think it's just, I think it's going to happen. So with the slow model, we were thinking maybe here's where we are right now, 2018 Q1, and then we'd spend another couple of months or a couple of quarters on refitting the Leonard-Jones and getting the infrastructure ready for doing large-scale QM torsion refitting. Right, Haya already has some very basic. For a single bespoke molecules torsion fitting that we think will scale now that she solved some efficiency problems, but we still need lots of QM data in order to actually do that. We need good ways of generating that QM data and storing it. Then after that, we'd be able to refit all the torsions and start to think about how we improve the charge models, etc. But in the meantime, all of this other work can be going on to get us ready for expanding types, using the Smirky samplers to figure out where we're lacking torsion varieties, things like that. Yes.
So, I mean, why don't you finish? I'm sorry.
No, go ahead.
Well, I mean, one thing that came up when we met here was in 2016 was this idea of working on a small coherent set of molecules that had a limited set of anticipated types.
And we have.
Right.
This is the Alkyd set.
Right. And so I just, maybe this is already sort of in your mind, but maybe if so, worth mentioning that, how much does it want to take a set like that and use it as a tractable test case to push through as much of the process as possible?
I think it's one of the things we're hoping to do is, again, develop useful work products that help in other aspects of this collaboration, but outside as well. So this Alkyd set is available. It's got, it doesn't really have compiled experimental data at this point, but we could in principle compile that. So if we figure that's a useful thing to use
Bryce
internally.
did figure out which
molecules
molecules
that's right.
were in thermal ML.
Yeah.
To clarify for people, this is a set of molecules, right?
Yeah.
Which
So it's
comprise
alkenes, ethers, and alcohols.
Yeah. So it's just a very limited number of anticipated
Atom types and bond types.
Right.
And,
Somehow peroxide crept back in.
So, but that's something that we can use internally to
Right.
validate tools as we're co-developing them. But we are thinking, this is a small molecule force field meant for actually deploying in the wild in
Exactly.
anger against drug-like targets. And the starting point, if it's no worse than GAF, is it's ready to go. And then we want to try to incorporate whatever we learn on more limited sets or as we're building these in a much more global flow.
Yeah,
So
part I think of the point of that is like, if you're interested in one of these things, you could get the machinery working and apply it in proof of principle
Yeah.
to Alkyd
Exactly.
and then publish on that.
Exactly.
And it
Yeah.
will work for everything else,
Absolutely.
but you have a nice bite-sized unit to publish.
Right, and also the other thing is that you'll get a sense of scaling. I mean, if it's
Yeah.
like if it turns out you need a lifetime of the universe to solve that one, you're in trouble.
absolutely.
Whereas if
No,
you
the idea isn't that you have to apply it to the real problem in order to get any papers out or,
Right.
or build anything. We want to start small. These projects incubate in
Right.
small teams or individually. They get some papers out describing the idea and the science and application in a limited domain.
Right.
And then at some point, working with the software developer, the software engineer, we scale it up and make sure it's robust enough to handle working alongside all of the other main workhorses that are being used to improve these parameters more globally.
right.
And at that point, we probably figure out
Mhm.
what falls down, what falls over, and what doesn't.
So I mean, I would like just for discussion in the course of the next whatever, propose that we adopt that set or some subset of that set for which we have data as a model case that we push through. Everybody should it's their
Is there something to be gained by using it as a standard? I mean, I
Mhm.
think we should have a variety of different
Mhm.
model systems that are appropriate for whatever we're trying to do. Right?
Mhm.
For Leonard Jones, it's great because there's only a few Leonard Jones types, but it's not going to really help you with the Leonard Jones type expansion because there's not a variety of Leonard Jones types, not a huge variety of them. There's like 3 or 4, and that's probably enough. So there's other test sets that are probably important.
Okay.
for-
Well, then maybe the discussion topic is test sets.
Yeah, no, I think that's
Yeah.
a great
Okay.
test sets or working sets for
Right, yeah,
sub
whatever.
problems.
Yeah, so I think
Interesting
the
subproblems.
intermediate ground you guys probably both agree on actually is we should use it a lot, but we don't want to use it when it doesn't make sense.
And it's not the only thing that's going to be useful. Bond charge
Yeah.
corrections is probably not the most exciting thing to
Mhm.
think about. There's probably other test sets that have much more interesting, but could still be small.
Right.
But have
Kalen
more
made
diversity.
Mini Drug Bank, which is a set of like how many
Yeah.
molecules?
360?
360 molecules that include all of the permafrost atom types that occur in Drug Bank. So
And
it's
all of this were not 99.
yeah, so it's a lot of atom types in a small number of molecules.
My philosophy has almost been the opposite, right? I have in OpenMM tools, which is meant for testing a bunch of different algorithms, we have a variety of different OpenMM tools.test systems where you can simply import in one line of Python something that is anything from a harmonic oscillator to an array of harmonic oscillators to a Leonard Jones system to kinase inhibitor bound to a kinase and explicit solvent. Making sure your method works on a variety of test sets is also very important, just so it doesn't you know exactly where it breaks or where it falls down. So I think we should really emphasize making clear in advertising where all of our test sets are, what they contain, Mini Drug Bank, Alkyd, any of these other things that might have a limited variety of chemical types but some interesting experimental data. That should be a big focus, is to make sure that that's not just something that we bury or use internally,
Right.
but it's actually available for us
Curated
to
test sets in some sense.
Right. And I think that should be a first-class work product of whatever it is we produce. A bunch of questions for you guys. New water model. Are you going to talk about that today?
I'll talk about that's really James' work.
Great,
I'll
perfect.
talk about it. I mean, it's not meant to. It's just a direction that I think is kind of interesting.
Because not on this list was where we develop a new water model alongside things, and that's something that we should really figure out how to prioritize. We can use force balance right now, which is a great way to hit the ground running. But in the overall scheme of things, how does it fit in? Should it just have an API where it interfaces with some of the open force field tools? Is it something that we'd like to bring into the umbrella at some point later on? I think that can be decided much later, but it's something for us to start thinking about. How quickly should we start to recruit someone who would act as a software engineer? I think we're already feeling the need. It would be great to have somebody in full-time in this position, so maybe we should just figure out how to hire someone. The software development practices, we were already talking about how do we get people up to speed with what we're doing right now. There's some information in the Slack, but we do need to get everybody on the same page as far as how we develop code in a way that's modular and testable, etc. And then I also have some questions about the Smirnoff proposed changes as well, if we have 5 more minutes. Are we too much into lunchtime? or-
Probably should break for lunch, I think.
Okay.
Mike, I have you in the agenda as saying something about the guy you have joining who's going to work on
Right, the
polarization.
polarizability.
But
Yeah.
should we do that right after we come back?
That's fine.
Okay.
Let's take a minute and think about lunch then, because we haven't decided where we're going, and also what to do with the food in the back. So I mean, options for lunch are the faculty club. There's also Price Center, which has I guess is open today. So there's like Subway, Panda Express, Indian food. I don't know, well, Mexican. Just like this typical student union type thing. There are also some dining halls. There's like a vegetarian place over at Newark. You might be able to walk. Or those are probably the. So what do people? Also, other people